So when we're trying to figure out symmetry, guys, if we know in our mind what this picture or what this graph function looks like, then we can have a better job of graphing it, okay, and deciding how it's going to be symmetrical. So linear. Linear is f of x is equal to x, or y equals x. We know that if your slope is positive, which is the value right in front of your x, not 1, but positive, we know that eventually our tails are here and here, yes? Doesn't, you know, where it crosses the y-intercept doesn't matter. It's where are the tails, all right? We know that if our slope is negative, we're doing this. Eventually our tails are in quadrants 2 and quadrants 4. Now this is considered an odd function. And it's odd because the highest exponent on this function is what? And 1 is a odd number. Not in front of the x, we're talking about the exponent. A function is either even or odd, and it is determined by the degree of the function. So let's review. The degree of the function is the highest exponent. And your options are either odd or even. So the degree of this linear function has a degree of 1, because the exponent is 1. And it is odd. So quadratic. By now, in our mind, we should know what a function that says whose highest degree is 2 is. What is that the shape of? You cannot tell me that it's linear. Chapter 4 in Algebra 2, where the book got really hard. Yeah, there's something very famous within St. Louis. Parabola, yes. Quadratic is parabola. What? Oh, okay. It's a parabola, okay? So if it is positive, we knew from last year that the tails are pointing up, correct? Eventually, you're in quadrants 1 and 2. If it was negative in front of that first term, we knew that it pointed down, and our tails were in quadrants 3 and 4. So this has a degree of 2. This is an even function. So the even function is either going up or going down. The highest exponent. No, there is always an exponent. In this case, it's understood to be 1. Yeah. So, I mean, if I gave you something like y equals 3x to the 5th minus 2x to the 6th plus x to the 8th, what would the degree of that polynomial be? Yeah, 8. And is 8 even or odd? Okay. And is it positive or negative? The term is positive because it's a plus x to the 8th. Y'all with me? Does this make more sense now? Okay. Cubic. All right, so here, cubic functions in your mind, you need to know what these look like. Cubic functions do this if they're positive. They hug the y-axis, always. Eventually, the tails are going up and down. So eventually, the tails have to be in the first and the third quadrant if it's positive. And if it's negative, it goes over to the second and fourth. So you want to remember that cubics hug the y-axis. Its degree is 3. It is an odd function, which means all odd functions are either this way or this way. Okay? So even functions, look at the highest exponent. Odd functions, look at the highest exponent. You're going to have, for an even function, You're going to have 2 as the highest, or 4, or 6. And if it's odd, you're going to look and you'll have 1, 3, 5. You've got stuff going on in the middle, but where the tails end will always be the same. That's the pattern. Okay? Okay, rational functions always look the same. We're going to be graphing these. Last year we learned to solve them. And the first thing we always determined is what happens in the denominator, because the denominator tells us what x can't be. So when you deal with rational expressions, you always look in the denominator to determine what x cannot equal. And for graphing purposes, that value that x can't be gives us what's called an asymptote. So what x can't equal gives us an asymptote. And an asymptote is an imaginary line that exists that the graph will always approach, but will never generally, this year, cross. Okay? The graph will approach this. So in this case, x can't equal 0, correct? Because that's what gives us an undefined function. All right? So if I'm looking at f of x is equal to 1 over x, I'm having that x can't equal 0, which is the y-axis. Now this also has a horizontal asymptote, and we'll get to that later on this year. And currently it's right here. But what your function looks like when it's positive, again, is in the first and the third. And if I'm looking at f of x is equal to 1 over negative x, or a negative value, where we know, again, we have the same asymptotes, what quadrants will you be in now? 2 and 4. Because when I plug in a value, if I plug in a positive value for x into this, won't I get a negative value for y? And if I plug in a negative value for x, won't I always get a positive value? Okay. All right, the last one that you want to recognize are your root functions, and there's 2 of them that we're going to address this year. And our root functions will always hug the x-axis. So a square root function, if it's positive, we'll do this. If it's got a negative sign on the outside, where is it going to go? Yep, it's going to do this. Remember, square root functions are the inverses of parabolas, aren't they? We talked about this last year. Parabolas do this, right? So if we want the inverse, we've got to tilt it on its side. But is this a function? Why? Because it fails the vertical line test, which is why we say it's either this portion or this portion. Okay? We're body graphing. You're making me flexible. Okay, the next one is the cubic root. And again, it will hug the x-axis, because cubes hug the y, right? So in cubics, we talked in my class about acting like an Egyptian. You know? Okay, anyway, moving on. Yeah. So if x is negative, y is negative, it does one of these. Or one of these. And I didn't say this before, but cubes and cubics have something called the point of inflection, where the graph turns. Inflection. It doesn't have an infection, it has an inflection. My L. So when we're looking at these, when we're going to be talking about symmetry, what we're talking about are 5 different kinds. The origin, the x-axis, the y-axis, and the line y equals x, so actually 4. Okay, today we're just talking about the origin, which is the most common point of symmetry. Okay, so symmetry and coordinate graphs about a point. Graphs can be symmetrical around a point. If M is the midpoint between the original point and P prime have reflections. So if this is my point of symmetry, if I go here, I can also go here. The distance is the same, but I have to put that point in the right spot. In other words, if I put my point here, the distance up does not exist to the distance down to get to that same place. Does that make sense? So that point of origin has to be placed appropriately for it to exist. So here, it would be here, because I can go across and here. I can go up and down. I can go left and right, and I'm going to get to the same spot. Okay? Where would I put my point of symmetry for this next one? Right in the middle. Where would I put it for the last one? In the middle is called the point of inflection. And this is a graph of what kind of a function? Is it a cubed or a cubic root? Which one hugs the y-axis? So this is an example of f of x equals x cubed. And our point of inflection is generally, if it's placed at the origin, is generally where it's going to be. Where our point of symmetry is. Mary? Because we talked about it right there. Okay? All right, where would I put it here? All right at the origin. Anybody know what this shape is called? It's 2 parabolas, right, facing away. It's called a hyperbola. Did we do this last year? Okay. Yeah, I thought we did. The end of the year. All right, so the most common point of symmetry is the origin. To determine if a graph is symmetrical on the origin, the graph has to follow the following rule. Get rid of this. This is wrong. And you have to memorize this. This is what we're trying to prove. And I'll show you what this means when we do some examples. F of negative x is equal to opposite of f of x. No, cross out the first one. That's incorrect. You have to memorize this. These are your tests that you're going to be using. If you don't know the test, you can't show me without whether or not it's symmetrical around a point. Okay? So, here we go. I want to know if f of x is equal to x cubed is symmetrical around the point. Is there a value that x can't be? Kind of give me a sketch of the graph. Let x equal 2 is what I'm going to say. We're going to do this with values so that you see what's going on. But ultimately, you have to prove f of negative x equals opposite of f of x. The numbers are just kind of your backup. Okay? All right, so we know that this is what shape? Buddy Griffith, where are your tails? Oh, all right, there we go. Okay? That's what it looks like in your mind. Do you think if I put this point here that this should be symmetrical around the origin? Okay. So we know in our mind it should be, right? So let's see if we can prove it. All right. Get rid of the negative x. And I lost some lines in here when this got transferred over, so put a couple lines in here. So f of x, that means do a substitution. So if f is 2, f of 2 is equal to 2 to the third, which is 8. My next step says find f at the opposite of what we let x equal. So what are we going to substitute in? Negative 2. So we're going to do f of negative 2. Well, that's negative 2 quantity cubed. This is where, if some of you guys have a really bad habit of not using your parentheses appropriately when you substitute, you will get signs wrong, which will get you the problem wrong. Okay? When you substitute, you have to use the parentheses in the right way. This is what? All right, I'm going to go up. Okay. Then the last thing that I try to get my final answer is what is the opposite of my f of x? Well, what's f of x? 8. At f of x, when we plugged in 2, right? Now we want to take the opposite of my answer at 2. Well, that's the opposite of 8, right? My answer at 2 was 8. I want to take the opposite of that answer, correct? Now, if it's symmetrical around the point, we said that f of negative x and negative f of x have to have the same value. Do they? Is it symmetrical around the point? Okay. So not only if it's symmetrical around the point. It won't always be. Okay? A point of symmetry. No, we're using 2 to prove it. You can use any point. But I'm not going to give you credit for using 2. You're going to get credit for showing the next step, which is the manipulation of the function with x in it. Okay? So this is what you want to do. What is at x? This is what we're doing. What is f of x? Well, f of x is equal to x to the third, right? What is f of negative x? Well, that is negative x to the third, which is what? Negative x cubed, right? And my last one says take the opposite of f of x, which is the opposite of x cubed, which is negative. Are these the same? So we will say yes, it's symmetrical about the origin. Mm-hmm. Yes. Okay. Uh-huh. And this is the one that you've got to really use. This is just for your own knowledge if you want to do it. You don't have to use a number, but you do have to use it with a variable. And that's what I'm going to look at to make sure that your work is right. Alex? Huh? All right. So let's get rid of 1 here again, just because of my lines. I'm going to put a little box here. In our mind, this is called what kind of a function? It's got an asymptote, but what's the name of it? Claire? Rational function, okay? So this is the parent function, so in my mind, it's positive. Which quadrants am I going to be in? And first and third. And we know we've got asymptotes along the x and the y-axis. Would you think that this would be symmetrical around the origin? If I go here, do I go that same distance here? Probably. If I go up here, I'm going to go probably down here, that same distance, okay? So it should come out. So if we do 3, f of 3 is equal to 1 over 3, correct? If I do negative 3, I'm going to get negative 1/3, correct? And if I do the opposite of f of 3, I'm going to do the opposite of 1/3, right, which is negative 1/3. These two are the same. Now let's do it with f of x. F of x is just the function that I gave you. What do I do next? F of negative x is 1 over, which is negative 1 over x, right? Right? Okay, what's my next step? Negative f of x, which is the opposite of 1 over x, which is negative 1 over x. Are these the same? So we're going to say it's symmetrical around the origin. All right, try example 3. Huh? This? Yeah, I just did it above it.
You don't have to do like actual points.
Just kind of look, yeah. Okay, so you got to remember from last year that the highest degree is also probably the number of times that it might cross the x-axis. The degree tells us how many solutions we have. Solutions represent our x-intercepts. Okay? But in this case, this is going to look, so it could look like this. If it's negative, where are my tails? First of all, even or odd? Okay, positive or negative? Where are your tails? Okay, 2 and 4, right. All right, so we know that we got a tail here and here. This is only going to have one solution because it's just x to the 5th. What's the only solution for when y is 0? X can only be 0. So it's doing stuff in here, but the tails are going to be here. So most likely, what do you think? Is this going to be symmetrical around the origin? Yeah, it should be. Okay. It's going to behave a lot like a cubic function because it's just a 5th root. All right, we're going to try it with a value. Pick a value for x. Okay, doesn't matter what you use. F of 2 is equal to the opposite of 2 to the 5th, which is negative. Y'all letting me do the thinking here. Negative 32. Okay. F of negative x. That's f of negative 2. That's minus, don't drop your negatives, guys. Negative 2 to the 5th, which is what? So all of this will eventually simplify down to positive 32, right? It's going to be the opposite of negative 32, but then that becomes a positive 32. Are you following my math? You got a frown, Allie. Okay. So then the next step is I'm going to take the opposite of what my f of 2 is, which is the opposite of negative 32, which is, are they the same? So now we're going to do it with f of x. F of x is negative x to the 5th. F of negative x is negative of negative x to the 5th. Order of operation. Am I allowed to combine these two negative signs together? I have to first take negative x to the 5th, right? And then, oh, that's just weird. And then change my sign. So some of you guys are going to get all messed up with your signs. Okay? And then the last one, take the opposite of what f of x is. Well, the opposite of f of x is negative x to the 5th, which is x to the 5th. Yes?
Give me an
this one? I'm just making sure that you can get them to work. And I'm going to show you one that doesn't work. Bless you. Okay, here we go. So x over 1 minus x. This is also a rational function. It's got a lot of other stuff going on. Technically, you don't know how to graph that yet. But what do we know that x can't be? We know that x can't equal 1 because that's what makes 0. Don't jump to the case that it's 0. It's what makes your denominator 0. 1. Because 1 minus 1 is 0, right? So x can't equal 1. So we would know that an asymptote would have to exist at 1. Would you agree? All right. So we're just going to do it with x. We're not going to do it with values. Okay? We're going to say that f of x is x over 1 minus x. It's just the function that I gave you, right? Now, f of negative x, I'm going to do that actually down here because I'm going to run out of room. Well, wherever there is an x, we plug in what? Negative x. So that's negative x up top and 1 minus negative x down below. Y'all with me? Because we're doing negative x. We're doing f of negative x. We're doing that. I'm just running out of room. Okay? Well, that's going to simplify down to negative x over 1 plus x. Now we have to do the opposite of f of x, correct? That's the opposite of what? Right. Okay, so then here's where y'all are going to make a mistake. Where do I put that negative sign? Do I put it both on the top and the bottom? Or do I put it on the top or on the bottom? Either the top or the bottom, but not both. Okay? Some of y'all are going to want to go, oh, I'm going to multiply top and bottom by that negative sign. No. Okay? Now, my question is, then, if I'm going to pull it to the top, I still get 1 minus x down below. Wouldn't you agree? So, is this exactly the same as this? If it's not, signs and everything. Remember, you can switch order, right? I can say 1 minus x, or I could say negative x plus 1, and that might sometimes be necessary to see that they're the same, okay? But are they the same? In this case, no. So we know that it's not symmetrical around the origin. It doesn't mean that it's not symmetrical around another point, just not the origin. This one is going to have a couple of asymptotes. It's going to have one at negative 1, positive 1, and it's also going to have one at, let me see, hold on, it's going to also have one at, sorry, not there, negative 1. And it'll still act like a rational expression. So you can see it's symmetrical about this point, right? Where the two asymptotes are intersecting, right? Y'all with me? But it's not symmetrical around the origin. Okay. Any other questions? All right. I would suggest that you get out that homework, because you are in your book, and you pair up with someone as you start working